Okay, hello everybody, and a very warm welcome to this fourth Nuclear Masterclass webinar. It is the final webinar of our pre-16 Nuclear Masterclass, although if you're doing the post-16 Masterclass, there'll be one more webinar for you next week. It's great to see so many of you joining us live. I think we've just gone over 132 people, so that's amazing. Especially tonight, as we've got such a great topic, and we're going to be exploring how we are recreating the process that powers the sun here on Earth. Now, if you haven't joined us before, I'm Dr. Elizabeth Cunningham, a former nuclear physicist, science communicator, and lover of Lego. I'm very excited to be here with you today to chair what I know is going to be a great talk. We're going to be exploring how we can recreate nuclear fusion. So, as I said, the way the sun generates power and how they're doing that using high-powered lasers here on Earth, and talk about whether this might form a clean energy source for the future. Now, our speaker tonight, we're very lucky to have Dr. John Pasley, who is a member of the York Plasma Institute at the University of York. He works on high-powered laser interaction with matter and inertial fusion related science. In his spare time, I'm told he enjoys photography and collecting, among other things, 1980s tech, and he's also acted in several Bollywood movies. So maybe we should ask him some questions about that. But that's enough from me. So now I'm going to hand over to John, who's going to tell us all about inertial fusion energy. Thank you very much.
Okay, brilliant. Thank you very much, Elizabeth. I appreciate that introduction. Hello, everyone. So I'm Dr. John Pasley. I'm speaking to you here from the University of York. And today I'm going to be telling you all about inertial fusion energy, which is the science of how we release energy via nuclear fusion using very large lasers. Okay, so this all starts off, I suppose one could say, with Einstein. So in the early 20th century, in 1905, Einstein published his very famous special theory of relativity. And as a part of that, he demonstrated that objects have an intrinsic energy associated with their mass. So in other words, it's not just about whether they're moving or whether they're in a gravitational field or something like that, but objects have energy associated with them just by their having mass associated with them. This is known as mass energy equivalency. And I'm sure you're all familiar with the equation because it's probably the most famous equation in the whole of physics. The energy is equal to the mass times the square of the speed of light. And what this means, because the speed of light is a very large number, it's 3 times 10 to the power of 8, that there's an enormous amount of energy associated with mass. So, in fact, 1 kilogram of mass is equivalent to 9 times 10 to the 16 joules. So that's 9 followed by 16 zeros. So a huge amount of energy. Another way of visualizing that is that if you were to take the energy of 1 paperclip and convert it into energy, it would release around 10,000 tons equivalent explosive energy of TNT, which will be more than enough to largely flatten the city of York, where I'm talking from. So I hope that doesn't happen. Right, okay, so it's a mass energy equivalency relationship that allows energy to be released via the processes of both nuclear fission and nuclear fusion. And the idea here, or how it works, is that the combined mass of the products is less than the mass of the reactants. So the difference is therefore releases energy. And in nuclear fission, what happens if you look at this little curve at the bottom, you're moving from you're moving from right towards the left along this curve, which is called the curve of the binding energy. And all the way down from the very heavy elements like plutonium and uranium, you can release energy by breaking up the atomic nuclei until you reach iron. If you've got elements which are lighter than iron, then you're able to actually release energy by going in the opposite direction. So by joining the lighter elements together to make heavier ones. Now, in nuclear fission, we're I suspect, all aware of examples of energy release via nuclear fission. This is used in nuclear power reactors, and it's also historically been used in weapons in the Second World War. Probably many of you will have seen the movie Oppenheimer, which is related to that. So fusion, however, that isn't something that we're currently able to do on Earth, at least not very, not on a very large scale like we can with fission. So it's something that we're still really working on. With fusion in the sun, fusion occurs over very long time periods because the hydrogen fuel that's used in the sun, or which exists in the sun, is not particularly reactive, so it doesn't burn very quickly. On Earth, we want to do our fusion as easily as possible, one could say. So we use the isotopes of hydrogen, deuterium, and tritium, which are far more reactive than basic hydrogen. And by fusing these two isotopes of hydrogen together, we can release quite a lot of energy via this fusion process because the mass of the reactants, which in this case, the products, which in this case are an alpha particle and a neutron, is less than the mass of the reactants. So the deuteron and the triton that are going into cause this fusion reaction. And the difference is released as energy. Okay, so neither fission nor fusion reactions produce greenhouse gases. However, fusion is by many considered to be preferable to fission because it produces very much less radioactive waste for a given amount of electrical energy released once you've converted the energy into electricity, that is. And also, being able to do nuclear fusion doesn't mean that you have to have access to the materials which can also be used to build weapons. So that means that you can have fusion power stations anywhere on Earth without there being any concern about undesirable materials falling into the hands of terrorists and things like that. Furthermore, we have sufficient fuel to actually power these reactors for millions of years versus probably only a few thousand with fission power. Okay, so hopefully we've established, or at least many people think, that fusion is a good way to go forward in terms of trying to produce energy. Now, the only problem with fusion, or one of the main problems with fusion, is that it's very much more difficult to achieve here on Earth than fission. With fission, all you need is a critical mass of material. You've probably come across this concept before. If you just had some little blocks of uranium-235 and you piled them up on your table in front of you, then eventually they'd start releasing very large amounts of energy via fission. You wouldn't need to do anything else. You just pile them up and they'd start releasing energy. Well, fusion's similar in the sense that you also need effectively a critical mass of fusion fuel. As I say, we use deuterium and tritium. But you also need to get that fuel to a critical temperature. Well, what's the problem with that, you may ask? The problem is that the critical temperature is in excess of 100 million degrees. And clearly, it's very difficult to raise materials to that kind of temperature. But furthermore, you need to actually put the materials in something. You have to have a reactor vessel to contain these materials whilst they're fusing, and no physical vessel can survive at anything close to those temperatures. Leads us then to two different approaches to actually doing fusion here on Earth. One of which is magnetic confinement fusion, which basically uses a kind of a magnetic levitation to suspend the burning fuel away from the walls of the reactor vessel. The approach that I work on is called inertial confinement fusion. And with inertial confinement fusion, we try and get the fuel to burn so quickly that it just explodes in a very tiny quantity near the middle of the reactor. And it does it so quickly, it burns the fuel so fast that the plasma, the hot material that's generated, just doesn't have time to get near the reactor vessel walls. And so you're kind of okay by not having to actually confine that material for a long period of time. So with magnetic confinement fusion, you want a kind of quite a gradual burn process. And it turns out that the rate at which fusion reactions occur goes with the square of the number of particles that you have per unit volume. So if you have a relatively low density fuel, it will burn relatively slowly. On the other hand, with inertial confinement fusion, you want extremely high density fuel so that it will burn incredibly quickly. And as we'll see, the confinement here is actually provided by the inertia of the fuel itself, which is why we call it inertial confinement fusion. It's here. Right, okay, so very often, in order to get the fuel to the very high densities, because you need a lot of, as I said, you need a lot of these particles per unit volume to get the reaction rate to be very high, you actually need to compress the fuel. Very often, to compress the fuel, we use high power lasers. There are other ways of doing it, but the only one that's been successfully implemented thus far employs lasers. Though very often you'll hear this approach to fusion being called laser fusion. Okay, we're kind of getting into quite an exciting period now for fusion in general. There's very large amounts of money being invested in both the magnetic confinement and the inertial confinement fusion approach. And we've actually already managed to achieve ignition and energy gain at what we call the target level from inertial confinement fusion, first of all in December of 2022, but we've also done it quite a few times since then. And the two large facilities that are, in the case of inertial fusion, already built, and in the case of magnetic fusion, currently being built in France, are the National Ignition Facility and ITER. Now, notice that when I said that we demonstrated ignition and energy gain, I said at the target level. So unfortunately, that doesn't mean that we're yet in a position where we can generate overall gain with respect to what we call the wall plug. So that just means that we could actually get out more energy from the fusion reactions than we've put in to the whole power plant or the whole laser system in this case, because it isn't really a power plant yet, in the form of electricity. So we're not at that point yet. That's kind of the point that we're trying to get to. Okay, so how does inertial confinement fusion work? Well, we use deuterium and tritium, as I said, because deuterium and tritium is very reactive compared to normal hydrogen. And what we do is we put it in a tiny capsule. This capsule is only a few millimeters in diameter. And this capsule has got three distinct regions. Now, you'll see on this slide that I've got in front of you here that there are three regions. The middle one is blue, and it's quite large. It takes up most of the volume of the capsule. And then around that, there's a yellow and an orange region. Now, these regions are not really those colors, but I've chosen those colors because actually everything's a very similar, rather transparent color in reality. So in the middle, you have deuterium tritium gas. Surrounding that, so what's depicted here as the yellow layer, is deuterium tritium ice. And you may wonder how you can have those two phases of matter existing at the same time. You can do that by holding the material at its triple point. So the triple point allows you to have all three phases, so liquid, solid, and gas existing at the same time. And that the temperature that you need to do that is very low. It's less than 20 Kelvin. So this is cryogenically cooled to a very low temperature. However, there's one more layer, which I haven't told you about yet, which here is depicted in orange, and this layer we call the ablator. Now, the way this system works is a little bit like a rocket. You're all familiar with rockets, whether from watching videos of NASA space launches or from setting off fireworks on Bonfire Night or on New Year's Eve. Now, with the rockets that you're used to, you have an exhaust going in one direction and the rocket flies off in the other direction. This system, although it kind of employs the same physics, has got several differences. First of all, because we've got our drive here, which comes in from all sides, so this is maybe a laser drive, or sometimes we convert the laser energy into X-rays. This drive actually heats up the entire surface of this outer layer, this layer that we call the ablator. That outer surface gets extremely hot and starts expanding. Now, you try and ensure that your illumination of this surface is as uniform as possible. So what that means is that rather than you having an exhaust going in one direction and the rocket flying off in the other direction, now you've got your exhaust coming off in all directions, which means that the rocket-like reaction to that expansion of the heated material is an implosion. So the rest of the capsule, which contains the deuterium tritium fuel, will now implode in upon itself. Okay, so that's what's depicted here. So you've got this very hot material. This is now in the form of a plasma, expanding out into the vacuum, which you have surrounding your fuel capsule, and that then implodes the rest of the shell to a very high velocity. The kind of speed that this reaches is something on the order, the implosion speed. So as I say, it's not flying off in any particular direction, but the speed at which this shell is actually collapses can easily exceed 400 kilometers per second. So it really moves very quickly. Now, the other difference to a regular rocket that you might be familiar with, like a chemical rocket, is that the ablator itself is just an ordinary material. It might be plastic, it might be another low atomic number material like beryllium. It doesn't contain the energy to drive its own expansion. So all of that energy is coming from this external driver. It doesn't need to be chemically reactive or anything like that. So the exhaust flies out, the capsule now implodes, and as it does so, the fuel that it contains, whether it was originally in the form of ice or in the form of gas, gets heated up and also very strongly compressed. The deuterium tritium ice gets compressed by about 5,000 times. And bear in mind, this is a solid material. So we're not talking about compressing a gas by 5,000 times. We're talking about compressing a solid, and that's really takes an awfully high pressure to do that. The gas region in the middle, which is kind of being squashed ahead of this imploding shell, gets heated up a little bit like the fuel in a diesel engine. But unlike in a diesel engine, which maybe gets to high hundreds of degrees, this fuel in the middle will be raised to a temperature approaching 100 million degrees. And at that point, at low density, because it is lower density than the surrounding fuel, it's actually still considerably compressed. That low density fuel will start to burn. And assuming you've met certain requirements that we'll talk about in a bit, that burn can then actually spread out into the surrounding fuel and consume a significant fraction of it, thereby releasing a lot more energy than you put in with your laser in the first place. Okay, so that's kind of the basics of how inertial confinement fusion works. There are two different ways that you can actually apply energy to your capsule. One of them is called direct drive, and the other is called indirect drive. Direct drive works pretty much how you'd probably expect this system to work. you shine your driver energy, be that a laser or something else, it could be an ion beam, for instance. You shine that driver energy at the surface of the capsule directly, as is illustrated here on the left, and that drives the process that I was talking about on the previous slide. An alternative way of doing this is to actually convert the energy of your beam light driver, which, as I said, could be a laser, it could be an ion beam, into soft X-rays. And the way this works is actually simply like a radiant oven. So, as you know, your oven at home gets to a temperature of a few hundred degrees, and the radiation that comes from the walls of the oven is in the infrared part of the spectrum. So if you were to look at your oven with a pair of infrared goggles or something like that, you would see it glowing very brightly in the infrared. The difference here is that we're raising the interior of this canister, this kind of rectangular object that you can see, it's actually a short cylinder. We're raising the interior of that canister to a temperature of a few million degrees. And at that temperature, most of the emission is in soft X-rays. So those soft X-rays fly around inside that canister. They're not directed towards the capsule, but many of them will hit it. And they also drive this ablation process, so this expansion process of the outside of the capsule, and thereby drive the implosion. Okay, so this is a picture of the National Ignition Facility, which is the only facility thus far which has actually succeeded in achieving fusion ignition and target level gain via inertial confinement fusion. It's a very large facility, as you can see. This facility contains 192 laser beams, and they're directed onto one of these canisters. This particular facility works via the indirect drive approach. The reason why they use indirect drive, by the way, is that by not having your laser beams fall directly on the capsule, it's actually easier to get the heating of the surface of the capsule nice and uniform. You could think about it a little bit like if you've got, as I have in my own office, lots of separate lights on the roof of the office, or on the ceiling rather. If you were to hold up a large piece of cardboard close to the ceiling, you'd see very defined spots near to the lights. But if I look at the floor of my office, I see it's very evenly illuminated. So in much the same way, even if there is structure in the actual laser beams, which are falling on the capsule, if you now shine those same laser beams at the interior of this canister, then all that structure will be lost by the fact that the light, or now the X-rays, has to propagate from the wall of the canister to the capsule. And this is the target chamber. So this is the vacuum chamber that you put your fuel capsules into on the National Ignition Facility. And this, apparently, I'm told, is the world's largest crane actually lowering it into position. This took place quite a number of years ago now. This is the target. So as you can see, the indirect drive approach. So the tiny spherical fuel capsule is surrounded by this cylindrical canister. And this coin is a small American coin called a dime, which is around about the same size as a 1p piece. So it's all pretty tiny. So essentially then, the way that you're managing to create the conditions for fusion is by having an enormous laser. That laser system is the size of 3 football pitches side by side, focusing all that energy down in a very short pulse, which is only 20 billionths of a second long, into a very tiny canister to create the very high energy densities that you need for fusion. Now, sometimes you'll hear discussed, rather than inertial confinement fusion, inertial fusion energy, which is the objective of the work that we're actually pursuing. Inertial fusion energy means not just doing what I've said in the previous slides, but also actually extracting the energy from your fusion reactions and using it to generate electricity. In order to do this, you have to actually ignite a large number of these fusion capsules every second. So you fire them in one after the other, and every time you fire one in, you fire the laser, the fusion capsule ignites and burns, and then you have to capture the energy. The energy comes out in neutrons, and so you capture the energy of those neutrons in the walls of the reactor, and at the same time, you use those neutrons to breed further tritium. Because one problem with using deuterium and tritium as a fusion fuel is that tritium doesn't occur in nature, so you actually have to make it. At the moment, it's made in fission reactors because they provide a plentiful source of neutrons, which is needed for making tritium. But if you actually have a functioning fusion device, then it can actually make its own tritium by kicking out a lot of neutrons, and those neutrons can then interact with lithium and make more tritium to power your reactor. Okay, so the current situation for inertial fusion energy is that the National Ignition Facility has demonstrated the potential for gain via inertial confinement fusion using indirect drive. But the problem with this is that, well, the National Ignition Facility lasers are solid state glass lasers, which means that they take a very long time to cool down after every time they've fired before you can fire them again. Basically, because every time you fire them, the glass warms up, and as with anything else that warms up, it tends to expand a bit, which changes all the optical paths. So this doesn't work. Such a laser like that doesn't work for a power plant because, as I said, you want to try and fire your laser multiple times a second. NIF can only fire twice a day, so it's not really going to make a very good power plant, even if you can get more gain out of your capsules. Also, the efficiency of the NIF lasers is very low. The NIF lasers use quite antiquated laser technology, which is only around 1% efficient. Fortunately, we can do much better these days, but that isn't the technology that we have in these existing facilities. Okay, so I want to tell you a little bit about the detailed physics of how the fusion reactions actually occur and how they spread within the capsule. So this slide shows you the deuterium-tritium reaction. And there's only one reason why this reaction is chosen. It's chosen because the probability of it occurring at temperatures that we can hope to achieve is much higher than for any other fusion reaction. It's around 100 times higher. So if you look at this plot here, this axis is on what we call a logarithmic scale. So it's not going up linearly, it's going up in powers of 10. So the deuterium-tritium reaction, which is shown here in blue, is far more likely to happen at a given temperature than these other reactions which are shown. Now, the deuterium-tritium reaction gives off both a neutron and a helium-4 ion, otherwise known as an alpha particle. So you've probably come across alpha particles before as radioactive products in your nuclear physics studies. Now, the neutron is what we actually use to get the energy out of our fusion device to actually make electricity and also to actually breed more tritium. But the alpha particle is what's important for the actual ignition and burn processes within the capsule. So first of all, you need to have ignition. The way ignition works is that the implosion, it creates essentially two different regions within the capsule. You've got a very high temperature, but relatively low density hotspot in the middle, surrounded by a much denser but cooler region of deuterium-tritium, which is at very high compression. That happens because of this collapse of this, not completely hollow because it's filled with gas, but this is what happens when you collapse a sphere. You heat up the material in the middle by compression to a very high temperature. This is good actually, because you don't want to have to heat up all of your fuel. Really what you want to do is only heat up a small part of it and then let the burn spread from that small region. A little bit like if you had say a wood fire at home, you don't want to ignite your wood fire by having to heat up all of the wood in the fire yourself to the ignition temperature. You want to ignite the wood a little bit of it and let the burn spread from that small piece of wood to the other pieces of wood in your fire, so that you're not having to ignite your wood fire at home with something like a jet engine. Okay, so you've got this central region which gets up to the conditions that you need for fusion. But in order for it to actually ignite, you need to have this central region be sufficiently large that the alpha particles that are released will tend to redeposit their energy in this central region. That then causes the temperature of this central region to rise to an even higher temperature. So it starts off at maybe 50 to 100 million Kelvin. But after a few picoseconds, if it's able to capture its, picosecond is a trillionth of a second. After a few trillionths of a second, if it captures its own energy from the alpha particles, this central region can heat up to a temperature of around 700 million Kelvin. And at this temperature, the burn can easily spread out into the surrounding much colder fuel, where the burn temperatures can reach over 1 billion Kelvin. Now, if you actually want to release a lot of energy, essentially what you need to do is ensure that you've got a lot of fuel for your burn to actually consume. Okay, so how do we do that? Well, essentially just by making sure there's a lot of fuel out there. So we have our central hotspot, and this is surrounded by this much denser fuel region. Now, fortunately for us, if you have something which you've compressed, if it's just left to expand, the way that it will do that is, rather than all kind of expanding uniformly, the outsides will start to expand first. And that wave of expansion will move into the more compressed regions, or the regions nearer the middle, at the sound speed in that material. But the sound speed here is extremely high. It's around 500 kilometers per second because the material is so hot. And so what you have is basically a race between this inward moving expansion wave and the outward moving burn wave, which comes from the hotspot. And there is no active confinement here whatsoever. The pressure that you can produce with your laser is very much less than the pressure of the burning fuel. So essentially, it just flies apart as fast as it can. But it can't fly apart instantaneously because the fuel has inertia, it has a natural resistance to motion, and that's why we call this inertial confinement fusion. And as I say, it's preferable that you start off with most of your fuel being cold, because you don't want to have to heat it all up with your laser. That wouldn't be very efficient. So NIF has demonstrated that you can do this process, that you can ignite it, you can get burn to happen. But as I say, it uses a technology which isn't suitable for a power station. It uses glass laser amplifiers. It's also too low repetition rate. And the fact it needs to be so large means that building a power plant based on this technology could end up being prohibitively expensive. So what we're doing in terms of trying to move forward with inertial fusion energy is, well, first of all, we need to develop targets which are a lot more, which are very inexpensive compared to the targets which are currently used on NIF, which cost many tens of thousands of dollars. You can actually, we think, build a target for about the same cost as a Lego brick. However, in order to do that, you need to make a lot of them. So essentially, your cost is reduced by just the fact that you're making a very large number. At the moment, all of the targets that we're actually shooting are essentially completely custom. So they're made to order in a rather time-consuming process. The lasers also need to have a very much higher repetition rate and be much more efficient than the NIF lasers. Now, we actually know how to build lasers like that. We just haven't built one big enough to actually do fusion with it. We also need reactor designs, and we have reactor designs, but we haven't really decided yet which is necessarily the best type of design, because there are lots of different options for how you could actually build an inertial fusion-based reactor. And this is one of the ways in which the magnetic confinement community are ahead of the inertial fusion community, in spite of the fact that their very large machine is still under construction. Because ITER, once it's actually built, will look far more like a reactor than NIF does. The reason for that is basically you have to solve a lot of the problems that you need to tackle in order to build a working power reactor in order to do magnetic fusion at all on a large scale. Whereas with inertial confinement fusion, you pretty much just need a box that you can put a vacuum in and then drop a target into it and shoot a laser into it. And that's about all you need to do to actually demonstrate the core physics. Well, we're doing work on these things. I'm not personally, I actually work more on the design of the fusion capsules, but we are developing very high efficiency, high repetition rate lasers. We're also working on target fabrication technology that will be far more cost effective, and also ways of actually injecting these targets into the center of the reactor accurately and at high repetition rate. Finally, as I said, we've got lots of different ideas for reactor vessels, some of which are illustrated here. And so there's lots of work to do. We're still quite a long way from an actual power plant, but the fact that we've managed to get as far as we have is really exciting. It's great that we've actually managed to get more energy out of these capsules than we've put in with the laser. Now all we need to do is get more out than we put in with electricity, and we'll be well underway to actually making a power plant. Okay, so my conclusions then. So we have achieved ignition in inertial confinement fusion, so we've got the fuel to burn, but there's still an awful lot of work to do to actually turn this into a working power reactor that can put energy onto the electrical grid. That's about all I have to say today, aside from answering your questions, which I look forward to. Thank you very much.
Well, thank you so much, John, for that fascinating talk. I really enjoyed learning about where we are in terms of fusion and its practicality and how close we are to making power, but how much progress we've made. It's really interesting. Thank you very much. We do have a lot of questions, so I'm going to move straight to them if that's okay.
Yep.
I just want to also remind everybody, because we've got already so many questions, we probably won't get to them all. So if you are doing the masterclass, please remember you can put your any unanswered questions onto the online question forum and they will get answered. So please remember your questions, and if I don't get to them. So there were some asked at the beginning, so I'll start there. There was someone interested in sort of what you mean by stable elements. So someone has asked, iron is in the zone of very stable elements. What does that mean? I mean, how is it different from stable element? Why do you say very stable? And then someone has asked, why is helium more stable than lithium?
So helium is more stable than lithium because if you look at the curve of the binding energy, it's not actually completely smooth. So it has peaks and troughs in it. And helium actually sits on a kind of a peak in the curve of the binding energy, which means that for how light an element it is, it's extremely stable. So it will fuse, but it's more challenging to make it fuse. And iron is indeed at the peak of the curve of the binding energy, and therefore is particularly stable compared to other materials.
Thank you very much. I have also been reminded to tell everybody that because we've had so many questions and there is a lot of interest in fusion, to say just to note that that we are running a 3-week course starting on the 6th of July that's open to anyone, and the course is just on fusion. And I believe the link has been put in the resources section. So if you're interested in joining that course, I think if you follow the link, you can give your email address, and then once the details are set, they'll be shared with you. But that will just a 3-week course just on fusion if you're interested to learn more. Because John, you've sparked a lot of interest in our audience today. Okay, so
hopefully I haven't just confused them.
No. Interest. So there's an interesting question. I think I know the answer, but I will put it to you. Someone's asked, is there any fusion that happens naturally on Earth?
Yes, there can be. you can potentially get very tiny amounts of fusion reactions in lightning strikes under some circumstances, we believe. Um, what happens in a lightning strike is you've got an extremely large current, and this causes tremendous heating, but also potentially you can get collapsed filaments of plasma, which are more extreme conditions than you might expect due to the magnetic pressure created by these very large currents. So, yes, but only in really quite minuscule amounts. With fission, of course, there at least has been a significant natural fission reactor, which was discovered. I mean, it hasn't been active for many millions of years, but it was realized that there was one by the fact that someone turned up effectively a load of very old radioactive waste, which predated, well, humankind. So with fission, it can happen, but not really to any significant extent with fusion.
Okay, very good. Thank you. I didn't know the answer to that question. Um, Someone has asked, how does magnetic fusion work differently to inertial? I think you did go on to talk about this, but maybe you could just summarize that for us.
So, I mean, there are many differences in the actual functioning of the physics going from inertial fusion to magnetic fusion. They both use deuterium and tritium. Um, there are some commonalities in addition in terms of the way you get the energy out. So you probably are going to try and capture the neutron energy in much the same way. Where it differs is really in the fact that in magnetic confinement, you need to hold a relatively low density fuel for a very long period of time, potentially indefinitely, whilst it gradually burns. So that means you actually have to have some kind of confinement of the fuel. You have to, effectively, what you do is magnetically levitate the fuel within the reactor so that it doesn't touch the walls of the reactor. So the fuel there is very low density, it's much less dense than air, and it's burning comparatively slowly. With inertial confinement fusion, you're using a very much smaller mass of fuel, but you're compressing it to many thousands of times its natural solid density. And so under those conditions, it burns in a few trillionths of a second. So the time scale for the burn is very, very much shorter in inertial confinement fusion. The density is very much higher. And also, actually, the temperature is higher because it's burning so quickly. But that's not such a sizable difference compared to the other things I just mentioned.
Okay, thank you very much. So someone is interested in sort of the practicality of scaling up inertial confinement fusion. So I said, how do we scale it up given that the targets are very expensive to make and they are and B that they are small and power generation is time is short.
Okay, so the way in which you actually try and go from where we are now to a working power reactor, first of all, starts with the driver, really. So first of all, you need a driver that fires at high repetition rate. That's something that we're quite close to being able to do. Getting the cost of the targets down, one of the main ways that you do that is by shifting from this indirect drive approach to a direct drive approach. Because indirect drive, as you might have gathered from the little diagrams that I showed you, involves more structures, it involves more material. It's quite a lot more complex because you have to have this cylindrical converting element to actually get the energy from laser photons into soft X-ray photons. So just by switching from indirect drive to direct drive, you immediately greatly reduce the cost of the targets, because rather than having this rather complicated device with lots of different elements, you now just have the spherical fuel capsule. However, that does also introduce some complications because that fuel capsule has to be kept in pretty much perfect condition on its way into the center of the reactor. We've got some ways of dealing with that, which essentially amount to putting the capsule inside something when you fire it into the reactor, and that something that it flies along inside separates out and leaves the capsule behind. But these are all problems that we're working on. I don't know whether we can actually make this work and produce. We can definitely make it work, but whether we can make it work and have the electricity be sufficiently inexpensive to make it competitive, that's a different question. And we don't really yet know the answer to that. But it's good at least to have as many options on the table as possible in terms of how can we solve our energy crisis for the future.
Thank you. So we've got some more fundamental questions I think that I'll put to you now. So someone has asked, how are laser beams actually created and how do photons influence matter?
Okay, so the way that you create a laser beam essentially is you rely upon a process known as stimulated emission. And the way stimulated emission works is essentially like this. You've got as you know, in your atom, you've got different electronic energy levels. And if you can excite an electron into a higher electronic energy level, it will then tend to naturally drop down. And as it does so, it will tend to emit a photon. That's called spontaneous emission. There are some materials where the electron kind of gets stuck part way down, dropping back into the position it started from. And if, whilst it's sitting there in that excited state, you fire in a photon which has got exactly the energy between where the electron is now and where it needs to get to in the atomic structure, then you'll actually kick out another photon going in the same direction as the original photon with exactly the same energy. Now, what happens in a laser is you get a material like that and you excite a large amount of that material all at once, and then you send one photon in at, well, actually lots of photons, but they get multiplied. But imagine it's just one. You start off with one, that kicks out another photon, that then kicks out 4 photons, and they very rapidly multiply as they go through the material until at the end you've got a lot of photons and potentially a lot of power. So that's how you make a laser. There are various ways you can excite the material. It could be with flash lamps, which are what are used at the National Ignition Facility. That only works if your material is transparent, because you've got to get the light in there to actually excite the atoms. You can also use electricity to excite your laser and various other techniques. Okay, so I'm not trying to give a masterclass on how a laser works, so I'll move on to the next bit of the question, which is how do you actually heat up your material using the laser? So that's actually that's a really good question, and the answer gets a little bit complicated in some ways, because if you look at the energy of a laser photon, what you realize is that the energy of a laser photon is less than the typical atomic energy gap that you need, or sorry, the typical ionization energy of the most weakly bound electrons in any atom that you care to think about. What that means is if you take one laser photon and fly it into an atom, the electron's going to get bumped up a bit, but it's not really going to do all that much. However, if you've got a really powerful laser with a really high intensity, you can do something called multi-photon ionization. And what happens there is that you kind of do a little cheat, whereas with the photoelectric effect, where you actually need to have sufficient energy in your photon to knock an electron out, you can cheat by getting the energy with multiple photons, right? So your laser photons come along in very large numbers and they start knocking electrons out of the atomic shells. And then what happens is, of course, a laser beam is also an electric and a magnetic field. It's an electromagnetic wave. So those electrons which have been ejected from the atom then start shaking up and down in the electric field and gaining energy, they slam into other atoms, and then you get a cascade of ionization, which turns large amounts of the material into a plasma very quickly. So that's how.
Well, thank you. Thank you for answering that. So someone asked a similar question about amplifying light in a laser, but they also asked, what's the highest highest power laser we currently make? Do you know?
Yeah, the highest power lasers that exist at the moment are on the order of about 10 petawatts. So that's 1 times 10 to the 16 watts. The biggest one I've worked with is about 1 petawatt. So that's 1 times 10 to the 15 watts. But there are now slightly bigger ones.
Okay, so quite powerful.
Pretty powerful, yeah.
Someone has asked, how is the energy that's captured turned into electricity? And someone else has asked a related question, do all reactors heat water to generate electricity, or is there a more efficient process?
So the standard approach is as the second question kind of suggests, not that different to what you do in most other types of power station. So the difference here is the form that the energy comes out of the reactor in. So it comes out in neutrons. Now, I said that with the neutrons, you need to do 2 things. You need to make tritium, but you also need to capture the energy. Now, the materials that you use to actually breed the tritium are typically light elements like lithium and beryllium. The beryllium you need actually because it multiplies the neutrons. It undergoes what's called an N2N reaction. So the beryllium is there because if you just had 1 neutron coming out, making 1 tritium, you'd kind of be in trouble because you'd need to have a 100% efficient cycle to keep your reactor powered. But by putting the beryllium in, you now get more neutrons for each incoming neutron, and so you can make enough tritium. But these materials are metals, so you actually need to melt them if you want to move them around inside your reactor. So what they do is they raise the metals, the beryllium and the lithium, they mix it together, they heat it up to hundreds of degrees, and then they flow it around the outside of the kind of inner wall of the reactor. Now what happens is the neutrons come flying out and they actually heat that liquid metal up to an even higher temperature. And then what they do is very much like what they do in a fission power reactor. They then route that liquid metal in pipes, obviously not directly, into an exchanger which also has water flowing through it. The water gets converted into steam, and that in turn cools down the metal, the liquid metal, to its starting point, and it gets sent round again. You also extract the tritium at some point in this cycle. Oh,
Okay.
the alternative routes. Yeah, sorry, I forgot about that part of the question. With fusion reactions, because some fusion reactions give out lots of energy in charged particles, some people are looking at using what's called direct energy conversion, where you actually take the energy of the charged particles directly and convert it into electricity. If you're using deuterium and tritium, however, you'd have to first convert your neutron energy into charged particles in order to do that, which is in itself somewhat inefficient. So that is another option that people are exploring, but it's not completely clear whether you would be able to actually do that in a working reactor. I guess at the moment we tend to favor the conventional approach, which is used in other types of power reactor, in part because we know it works.
So you asked that question has prompted another one, which is what stops tritium from absorbing another neutron to make a new isotope?
What stops tritium from absorbing another neutron? Well, I mean, it isn't actually a reaction which is probable for tritium to absorb another neutron. I'm not even sure that it's actually allowed by nuclear physics for tritium to directly absorb another neutron. Actually, Elizabeth, you may know the answer to that better than me as a nuclear physicist.
No, I think the cross section is low. We can say that.
Yeah.
Um,
Yeah, so that isn't a probable reaction to occur.
Cool. Okay. So someone else has asked an interesting question. So it says helium-3 is made from lithium-6, which is only 7.5% abundant. It's only a 7.5% abundant isotope. And it must be enriched to greater than 40%. Is this process difficult and is it environmentally dirty?
Well, that isn't something that I really know the answer to be quite honest. That's not an area that I work on myself. I know that it is certainly possible to enrich lithium to have more lithium-6 in it, but I'm afraid I really can't comment upon how environmentally friendly or otherwise it is, because it's not something I know enough about.
Okay, thank you very much. Um, Another interesting question is, did nuclear fusion occur in the Big Bang?
Ooh, now that's a really good question because
Mm.
I also actually teach cosmology. So nuclear fusion did, of course, occur in the early universe, but not until uh, quite a period of time, in seconds at least, after the actual moment of the Big Bang. Um, the universe needed to cool down enough that you actually have stable nuclei starting to form. So you start off with, well, you start off with something very exotic, then it becomes a quark gluon plasma that then starts separating up into neutrons and protons. And then those neutrons and protons need to actually interact. And what you find is that you do get fusion reactions, and everything kind of settles down after a period of time into either just hydrogen, or all the neutrons end up swallowed up in the helium-4. Um, and one of the actually, well, probably the strongest piece of evidence for the Big Bang is the fact that if you look at the very early universe, you can see that which you can do by just looking a really long way off, you can see that the ratio of helium-4 to hydrogen is exactly what you would expect for a universe that starts off extremely hot. So that is very strong evidence for the Big Bang having taken place.
Very good. Okay, so we're going to go to from the Big Bang to stars. If a star ran out of fuel for fusion, could it be powered by fission?
No. Um, so so basically, what happens in a star is that you get to the point where it depends how big the star is, what you actually end up with. But if it's a very large star, then the core can burn as far up the curve of the binding energy as iron and nickel, which is, of course, at the peak of the binding energy. Um, at that point, the core of the star is no longer producing energy, and so it tends to collapse down. And if it's a very large star, it will then tend to either collapse down to form a neutron star or form a black hole. The rest of the star is blown out into space as a supernova explosion. So essentially, what happens is the core can no longer support its own gravitational attraction. That collapses, and then there's a rebound shock. So the core kind of comes in, and then a shock bounces out, and it blows the outside of the star off into space. Now, that process does actually generate fissionable heavier elements by a variety of processes. But they're now being blasted into space, and the concentrations are much too low to actually make it viable fission reactor fuel.
Okay, thank you. Now, I've been resisting asking this, but several people have now asked, what movies were you in?
Okay, so I filmed for two movies, but unfortunately, my part in one of them got left on the cutting room floor, which was very disappointing.
Outrageous.
But the one that I actually, where you can quite easily find me because this movie is even available on YouTube, is called Bang Bang, and it was released in 2014. And it was one of the biggest, like, it's a big blockbuster Bollywood movie in that year. It had apparently the biggest car chase of any Bollywood movie to that date. I think it had like 300 cars in this car chase. Yeah, and I actually played two roles in that movie. I was a mafia gangster and also a police officer. But when I was a police officer, they kind of downlit me and I had a little helmet on, so you couldn't see my face, which would have been a bit confusing because I actually had a shootout with myself. So if you'd been able to see it with me, that would have been a bit weird.
Oh, well, I think we're going to increase. Everyone's got to search that out now. So we're going to, yeah, increase the YouTube hits on that movie. Okay, so there you go. So don't forget to look up that movie, and then also don't forget the link to the online fusion course in the chat if you want to do that. Okay, well, that really is all I have time for. I've overrun a little bit because I wanted to find out about the Bollywood movies. Sorry we didn't get to all the questions, but if you didn't get your question asked, please put it in the online question forum if you're on the masterclass, and it will get answered. So this does wrap up our pre-16 masterclass webinars. So thank you to everybody who's been coming each week for that. But for those of you who are on the post-16 masterclass, we hope that you will join us next week when we hear from Dr. Nicola McConkey from Queen Mary University of London, and she's going to be talking about the mysterious particle, the neutrino. So it just remains for me to say thank you for joining us. It's been great to see so many of you, and enjoy the rest of your evening. Thank you very much.